Hey, geometry, having sound troubles. Oh my. This is the last lesson video of the year. Can you believe it? Oh my gosh. Okay, I'm hoping that these sound problems go away. Anyway, hi. Last lesson video. Now, it could be that we have another like review video or something, but this is the last new thing that you're going to get all year. Oh my gosh, it's the last one. So let's pause this last lesson video of the year and solve that warm-up. Go. Okay. So hopefully I don't have sound issues the whole time, because that would be fun. But basically you're trying to find the value of theta. And when you have a right triangle and you have two side lengths and you want the value of an angle, you're going to use inverse trigonometric ratios. And so the basic process of using inverse trig is a lot like using regular trig. It's just that you're going to be using that information in a slightly different way and slightly different buttons as well. So the first step is always to identify theta. So there it is, right here. And then across from theta is the opposite side. The hypotenuse is always across from the right angle, leaving the other side to be the adjacent. And once you have your sides labeled, in this kind of a problem, you're going to be kind of identifying what you have. You need two sides to solve for an angle. And so those two sides that we have information about are the opposite side and the hypotenuse. Now that helps us decide which trig ratio we're going to use. There's three. There's the sine, the cosine, and the tangent. The sine can be remembered with so, the tangent with ca, and the cosine with ca, and the tangent with toa. And since we have both the O and the H at this point, we should be getting pretty good at choosing the right trig ratio. We need the sine ratio. And what we want to do is use SOH to build an equation. The sine of the angle is the opposite over the hypotenuse. Oops, almost drew an H. The sine of the angle is the opposite over the hypotenuse. Now I'm off to get a calculator, and that's why this is taking a little while, and probably get all feedbacky as usual. So the first step is to take 7/10 and to turn it into a decimal so we can work with it. And so we have sine theta equals 0.7, and I actually didn't need that calculator at all. Now I could go over to my trig tables and look up 0.7 and find the sine column and figure out what angle that is. But as you've seen, that's not exactly an exact science, because you might find the angle of a measure that's like in between the ones that are on the list. And so what we could do instead is use what's called sine inverse. Now, what we're doing here is actually creating a cancellation by, and I'm going to say multiplying, even though it's more complicated than that, multiplying both sides by the sine inverse ratio. What this does is gives us something to put in our calculator. It also cancels what we want to cancel. We want to get rid of that sine function, and so we know that theta is going to be the inverse sine of 0.7. So we're going to plug that into our calculator. Now on this one, I have to put in 0.7 and then second sine and 44.43 degrees. And there we go. That's how you do it. The only tricky bit really is getting used to the idea that you are using those sine function buttons, those inverse sine buttons. All right, let's move on. So this might be the last time you update your notebook, y'all. Write yourself some questions, or write yourself some summaries. Maybe before you take the last test, you'll go in and do it again, but this is the last time I'm going to tell you to do it. Start a new note page and let's get going. Essential question today: how can you completely solve a right triangle? And the topic is solving right triangles. We are going to be taking everything we know that we've been studying this whole since gosh, I can't even think when it was, maybe even since spring break, and kind of put it all together. This is where we're going to take the Pythagorean theorem and the triangle sum theorem and trig ratios and inverse trig ratios and use all of them in a single problem and what we call solving right triangles. So here we go. So when you're going to solve a right triangle, you're doing something specific. The definition of that is when you have found all of the side lengths and all of the angle measures of a right triangle, you have solved the right triangle. If you're taking notes, now might be a good time to pause and write this down. I'm trying to make this video go a little bit faster, so I'm not writing everything out. When you have found all of the side lengths and all of the angle measures of a right triangle, you have solved the right triangle. So that's what we are going to be doing. We're going to be solving right triangles. In other words, we're going to be getting all the side lengths and all the angle measures, and that's what it means to solve a right triangle. There is some information you need to know when you are solving a right triangle. You can solve a right triangle if you have two side lengths. Let's just start there. If you know two sides of a right triangle, you can know everything else about that right triangle. Because if you have two side lengths, you can use Pythagorean theorem to get the third. You can use inverse trigonometry to get an angle. And then you can use triangle sum theorem to get the third angle. I know, we'll talk about it some more. But you have everything, all the tools in your toolbox if you have two side lengths. You can also solve a right triangle when you know one side length and one angle measure. So say you know this and this. Well, from that, you can definitely find the length of another side. You can also find the length of the measure of an angle, and you can use Pythagorean theorem to find the length of another side. So when you have these two conditions, either two side lengths or one side length and one angle measure, you can find anything else about that right triangle. So in order to solve a right triangle, you're essentially going to be using four tools. You won't necessarily use all of them, but these are the four that you will choose from. The first thing is the Pythagorean theorem. If you know two side lengths of a right triangle, you can always find the third because you can plug them into Pythagorean theorem. You're also going to use the triangle sum postulate, which says all three interior angles of any triangle sum to 180. This is what you use when you know two angles and you need to find a third because you're subtracting from 180. You're going to be using trigonometry ratios because you might know an angle and a side, and therefore you're going to need trigonometry ratios. And then inverse trigonometry ratios. If you know two sides and you want an angle, that's where inverse comes in. You are going to be choosing between these four tools every time you go to solve one of these problems. So let's just do one. So first of all, notice I have a right triangle. The instructions are solve the right triangle, which means I need to find all side lengths and all angle measures. It also says round decimal answers to the nearest tenth. So clearly we're going to be expressing some stuff in decimals. So in order to solve the right triangle, I need to find that side that's marked C. I also need to find all the angle measures. So you can really start this any way you want. I'm going to go ahead and find side C. Now if I have two side lengths and I want a third, I can throw those into the Pythagorean theorem, making sure that I put all the numbers in the right place. Now this C is the hypotenuse, and so I could say that 3 squared plus 2 squared equals C squared, which is the side I'm trying to find, and it's the hypotenuse, so this is a pretty straightforward use of the Pythagorean theorem. 3 squared is 9, plus 2 squared is 4, equals C squared. Don't forget, you have to square first. Please don't say that C is 1 squared. It's not. You don't, or 5 squared. Hopefully you can see why I'm saying that. You got to do the squaring. Now we're going to do the adding. 9 plus 4 is 13 equals c squared. And then we're going to have to take the square root of both sides. And so the square root of 13, oops, come on, calculator, is 3.6. And so we have found C. Okay, 3.6. So that's one thing we have to do. Now we have to get all the, we have to get the angles. So we know that angle C is 90 degrees, but let's find angle A. Now, in order to find angle A, I need two side lengths, because if you have two side lengths, you can find an angle. This is the angle I'm looking for. Oh, this board is like not calibrated, so it's not writing my stuff correctly, but we'll press on. So I'm going to choose, I could choose any one of these sides, any two of these sides. I could use the side marked with the 3 and the side marked with the 2. I could use the 2 and the 3.6. I could use the 3.6 and the 3. I could use any two angles to solve for theta, angle A. I'm going to use the 3 and the 2 because they're nice whole numbers. And I'm going to notice that across from theta is that 3, that's the opposite side. Across from the right angle is the hypotenuse, leaving this side with the 2 to be my adjacent side. Gosh, my board's not writing very well. Now notice that I have the opposite. I also have the adjacent. And so given that there are 3 trig ratios, the, I'll do this over here, the sine, the cosine, and the tangent, and the sine is the opposite over the hypotenuse, and the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent, I have both the O and the A, and so I'm going to choose the tangent ratio for this particular problem. And I'm going to set it up. The tangent of theta, which is what I'm trying to find, is the opposite 3 over the adjacent 2. And now I'm going to solve this just like I did in the warm-up. The tangent of theta is 3 divided by 2. 3 divided by 2 is 1.5. Now I want to get rid of that tan in front of theta, and so I'm going to quote-unquote multiply both sides by the inverse of tangent. So I have tan inverse times tan theta equals tan inverse of 1.5. These quote-unquote cancel, and I have theta equals the tan inverse of 1.5. 0.5, oops, 1.5 second tan 45. Oh, interesting. So I know that angle A is a 45-degree angle. So the last thing to do is to find angle B. Oh, sorry about that, 45 degrees. Well, that's easy because I know that angle B, if I take 180 and I subtract angle C and angle A, I'm going to get angle B. Well, 180 minus 90 is 90, and then 90 minus 45 is 45. And so we know that angle B is 45 degrees, and we have now completely solved that right triangle, because we know all side lengths and all angle measures. 1. All right, shall we do another one? So again, we're going to take a look at the situation we have and then choose the right tools to solve this problem. So we have right triangle JGH, and we know one of the angles is 25 degrees, and we know one of the sides is 13 degrees, and we're going to need to solve for all of it. We're going to need to find all of it. Well, let's see. If you know 2 angles of the right triangle, of any triangle, you know a third. So I'm going to start with angle G. And you can start anywhere, whatever you want to find. Angle G is going to be 180, minus 90 because there's a right angle in there, so that leaves over 90 degrees. And then I got to get rid of 25 degrees, and so 90 minus 25 is 65 degrees, and that is the measure of G. 65 degrees. And we're off and running. Now let's see. I can find either the side that's marked with a G, a little g, or the side that's marked with a little h. It doesn't really matter because I've got all my angles and I've got at least one side length, and so I'm probably going to use trig. I'm definitely going to use trig, and it wouldn't matter which angle I choose, but I guess I'm just going to go ahead and use the one that's marked 25 degrees. I don't know, you could definitely use the 65 degree angle too. It really wouldn't matter. But what I'm trying to find is the side marked G. That's what I'm going to try to find. So in order to find G, I have to notice that I have a theta of 25, and across from theta is my opposite side, that's over here. And then this is the hypotenuse, and oops, oh my gosh. I'm so distracted by those noises, the worst. There's the hypotenuse, and this is the adjacent. So I have the adjacent side. I'm trying to find the adjacent side, and I want the hypotenuse. And so I can use the sine, the cosine, or the tangent. The sine is so, the cosine is ca, and the tangent is toa. So I want this side here, and I have this side there, the a and the h, so I'm going to use the cosine. So that means the cosine of the angle, the cos of 25, that's the angle that I've set everything else up from, is the adjacent G over the hypotenuse of 13. And now I've got my equation, so the first thing to do is turn cos 25 into a decimal, 25 cos. Let's see, I'm going to clear that and make sure. 25 cos, yeah, 0.9 equals G over 13. Now I'm going to multiply both sides by 13 to clear that denominator, and I will have the measure of G when I take 0.9 and I multiply it by 13. I've got 11.7. All right, so there is G. Now I can find side H, get rid of a few things, make this a little prettier. I know that G is 11.7. So I can find side H because I know two sides of a right triangle and I want the third. Side H. Because I have Pythagorean theorem. Let's see, h squared plus 11.7 squared equals 13 squared. Do you see why I set it up that way? Remember, the hypotenuse goes here, and 13 is the hypotenuse, and so that's where it goes. So h squared, I'm going to leave alone, plus 11.7 squared. 11.7 squared is, making sure, 11.7 squared, 136.89. Let's say 136.9. Come on, Miss White. Equals, and what's 13 squared? 169. Great. Now to get h squared by itself, I'm going to subtract 136.9 from both sides. These cancel. I have h squared equals 169 minus 136.9, 32.1. And now I need to find the square root of both sides, and this problem will be done. H is on that side, and then the square root of 32.1 is 5.7-ish. And we're done. Because I found all side lengths and all angle measures. Boy, this board isn't working very well. There we go. So as you can see, it all kind of depends on what you need, what tool you're going to use. You're always going to use some combination of the triangle sum theorem, which is this one. Because if you take the angles and you subtract from 180, you get the other angle. If you have two angles, you can get a third. You're going to use some trigonometry, like in this one. Because if you have one side length and one angle measure, you can find another side length. And then if you have two sides and need a third, you might use the Pythagorean theorem. So in this particular case, I used those three tools. On the previous problem, I started out with Pythagorean theorem because I had two sides and I was getting a third. Then, in order to get an angle, I used inverse trigonometry because I had two sides and I needed an angle. And then to get that last angle, I used the triangle sum theorem or triangle sum postulate that made it so that I could just subtract from 180. So that's how you do these problems. You're going to choose from these four tools. You're going to use the Pythagorean theorem, the triangle sum postulate, the trigonometry ratios, and inverse trigonometry ratios. You will be choosing from just those four tools. Depending on how the problem is set up, you'll start with one or the other, and you'll just choose the right one out of your toolbox. And with this problem, when I had two sides, I used Pythagorean theorem, inverse trig, and triangle sum postulate. On this problem, when I had one angle and one side, I used triangle sum postulate, trig, and Pythagorean theorem. So it all kind of depends on what you're given. That's what makes these problems a little bit tricky because there's a lot to choose and a lot to think about. So we're going to do one more and then we'll be done. So in this problem right here, there are two sides. And I know in order to solve the right triangle, I need all three sides and all three angles. Well, if you have two sides of a right triangle, you can always get the third by using the Pythagorean theorem. So that's where I'm going to start. Side DE. Let's see. I know that that side DE is the hypotenuse of the right triangle. So when I set this up, it's going to be 20 squared plus 21 squared equals, and I'll just call this side x for now, x squared. So 20 squared is 400. That makes sense. Plus 21 squared is 441 equals x squared. Now 400 plus 441 is 841 equals x squared. Taking the square root of both sides, on this side I have x, which is what I'm trying to find. And then if I take 841 and find the square root, which is 29, I have found my first side. So I know that this hypotenuse is 29 units. And that's the first bit. Now, I found all three sides, so now I need to find an angle. And it doesn't really matter which one I choose. I think I'm just going to go ahead and throw a theta into E. It's the flattest theta ever. And I can use any of those sides, the 20, the 21, the 29. I just need two. So I can choose that as I go along. What I'm trying to find now is angle E. And I know I'm going to need to use inverse trig. So across from theta is the side that's marked 20. Across from the right angle is the side that's marked 29, leaving the 21 to be the adjacent. And I can literally choose any of those, two of those, in order to solve this problem. I'm going to go ahead and use this one and that one. I don't know. That's just what I feel like. You could use the adjacent. You could only need to pick two. There's three trig ratios, the sine, the cosine, and the tangent. Sine is remembered with so, tangent is remembered with ca. Sorry, why do I keep saying that? Cosine with ta and tangent with toa. So I have the O and the H, and so it looks like I'm going to use the sine ratio for this. So again, we remember that we want to put in the sine of the angle, which we don't know yet, is the opposite 20 over the hypotenuse, which is 29. Now we've got our equation, we can start to solve it. The sine of the angle is, and what's 20 divided by 29? 20 divided by 29 is, let's say it's 0.69. What does it say? To the nearest tenth? We could go as far as 0.7, I think, then, if we're rounding to the nearest tenth. And now we want to get at that angle, so we need to get rid of the sine ratio. So we're going to apply the sine inverse to both sides. In other words, we're going to take that sine inverse, and we're going to apply it to this side and this side, and that causes that cancellation. And so we have the angle is going to be 0.7 second sine to get that inverse, and it appears to be a 44.4 degree angle. And there you go. So we can get rid of some of this mess. This side was 29. And we can comfortably say that this angle here is a 44.4 degree angle, which means we just need to find this angle up here. But that's not a problem, because we can find angle D by subtracting from 180. We already know we've got a 90 degree angle here. So it's going to be 180 minus 90, which is 90. And then we got to subtract out this 44.4. 44.4, and let's see, 90 minus 44.4 is 45.6. And there you go. There's your last angle measure. 45.6. And that is a solved right triangle. Again, you're only going to use 3 tools, but they come out of those 4 possibilities. In this one, I use the Pythagorean theorem, and then some inverse trig, and then the triangle sum postulate. All right, y'all, that is solving right triangles. Your practice is going to be on Big Ideas Math. Last Big Ideas Math assignment, I think. I'm pretty sure. Anyway, I hope you have a good one. Sorry about all the squawking. See you later. Bye.